Hello and welcome to the first chapter, the first real subject of that course on machine dynamics, and that chapter is entitled Vibration Isolation. So when we study vibration isolation, our machine that we will consider in that course of machine dynamics is just a rigid block of mass. So a rigid body, and we in general study just 1 degree of freedom of that body. Sometimes there might be an additional mass, but the machine is just a single block of mass, and we study that machine as having 1 degree of freedom. So where does then the motion comes from? Well, there is the machine on the one hand, and there is the foundation on the other hand. And in between that machine and that foundation, there is a flexible connection that might have a stiffness and a damping. And now there are 2 important questions. If we study active vibration isolation, then what we study is we assume that there is some motion of that machine due to some forces that act on the machine. And due to that motion, part of that motion will be transmitted to the foundation because of that flexible connection between the machine and the foundation. That might create, for example, some disturbances on the foundation, some kind of noise, for example, some kind of vibrations, and that might be unwanted. So we would like to reduce active vibration isolation. We would like to reduce the influence of the motion of that machine on the foundation. In some cases, also the opposite question is of importance. There might be some vibrations of the foundation. So for example, in that building where I'm here, that's building 1023, there is the street, and on that street there's a tram, and if a tram passes on that street, then if we do some measurement here in that building, we would see the vibrations of that tram in our results. Of course, this is unwanted if we want to do measurements of some kind of vibratory systems. Therefore, what we need is some kind of passive vibration isolation. So we would like to isolate the machine and the foundation against vibrations of the foundation. Here we would like, in active vibration isolation, we would like to isolate the foundation against vibrations of the machine, and passive vibration isolation, we would like to isolate the machine against vibrations that take place or are transmitted from the foundation. So the objective is for both cases is the same. We would like to get some kind of reduction of the amplitudes of the excitation, for example, of the forces that excite the machine, of the amplitudes of these excitation forces that act on the machine. And we would like to see less amplitudes, for example, on the foundation. That would be a good active vibration isolation. The same for passive vibration isolation. There are some kind of amplitudes of the motion of the foundation, and we would like to see less amplitudes or smaller amplitudes for the displacements of the machine. In general, the variable that is then manipulated or changed is the stiffness of the connection between machine and foundation. We can, in an engineering mechanics context, we can symbolize that variable by a spring stiffness. In general, that spring stiffness is some kind of element between the machine and the foundation. That could be steel, that could be some kind of rubber element, so to have a very soft material, and so on. So you could select some kind of material in order to realize that stiffness between the machine and the foundation. In that chapter, I would like to treat with you 3 different subjects. The first one is active vibration isolation for a harmonic excitation of the machine. So there is a harmonic force acting on the machine. The machine itself is, as I said at the very beginning, represented by a rigid block of mass, and we study the effect of that harmonic excitation that acts on that rigid block of mass on the foundation. So whether that force that acts on the foundation is large or small. The amplitudes of that force are large or small. Next, I will move to passive vibration isolation, also for harmonic excitation, and I will study with you the vibration absorber, which is a 2 degree of freedom system. Having two masses, one mass is just designed to absorb the vibration that are exerted on the other mass. So that would be an example for passive vibration isolation. So here we have a harmonic excitation of the foundation, for example, or as a force acting on one mass, and we have some kind of absorption mechanism, or we manipulate the stiffness of the connection between machine and foundation in order to reduce the vibrations of the machine of our object of interest here. And finally, because as in both cases we study harmonic excitation, I will move to transient excitation. And I will just study active vibration isolation for transient excitation. As I said in the last lecture, this is just what happens in the foreground. So there is an application, namely vibration isolation. So the connection between machine and foundation is in the foreground. And in the background, some theory develops, namely the theory of the single degree of freedom oscillator. So first of all, I will repeat by studying active vibration isolation for harmonic excitation. I will repeat what you know about forced vibrations of the single degree of freedom oscillators. Then we will move here also to an example of a 2 degree of freedom oscillator. And finally, we extend the theory of the single degree of freedom oscillator from harmonic excitation to transient excitation. And I will promise you, you will rediscover some subjects that you have seen in control measurement and control theory, namely the weighting function, for example. So in that video, I will start with the first subject now, and I will study with you the active vibration isolation for harmonic excitation. And as I said, we will consider that machine as just being a rigid block of mass. So the mass is denoted by m here, and the connection to the foundation is represented by a spring with stiffness c, and there could be also some kind of damping element, so a damper with damping constant k. The force is a harmonic force, and here in that example it acts directly on the mass. So we have an excitation by an external force, and that external force is applied directly on our machine, so on our rigid block of mass. In a first step, I would like to compute the displacements of that rigid block of mass, and by compute, I would like to repeat what you know already about the displacements of that rigid block of mass from engineering mechanics 3 and 4. And I would like to study the particular solution, and then I would like to use that particular solution in order to compute the force with which the mass, basically by the spring stiffness or by the spring element and the damper element, acts on the foundation. And I would like to discuss with you how to change the spring stiffness or adapt or design that spring element so to reduce the force that is exerted by the machine, so by that rigid block of mass, via that connection to the foundation. So, and I would say this is the new thing. Studying the displacement x here is something you have seen already in engineering mechanics, but applying that knowledge to the design of that connection between a machine and the foundation, that should be something that is new, and that is what you can learn from applying single degree of freedom oscillation theory to that practical example. So let me start with the equation of motion that is, I guess, known to you or could be easily derived by you. So first we have the inertia term with the mass times the acceleration. Then next comes the damping term, and then we have the stiffness term. So these are the two restoring forces coming from the damper and the spring. And on the opposite side of the equation, so on the right hand side, we have the external force F of t. Well, as I said, the external force should be a harmonic force, and therefore I represent that external force by an amplitude F naught and a harmonic term, which is chosen here to be the sine function, and some kind of excitation frequency, capital omega. Usually, as you have seen in engineering mechanics, this is not the way how to study that equation. That is just the way how to derive the equation of motion. But in order to study the ordinary differential equations, we introduce dimensionless parameters. So we divide the whole equation at the mass m, and we introduce the natural frequency, which is denoted by omega naught here, and which is the ratio of c divided by m, the square root of c divided by m. So we divide the whole equation by m and introduce here omega naught squared. And for the damping term, we introduce the damping factor, capital D, by setting 2d omega naught to k divided by m. And on the right hand side, for f naught divided by c, we introduce y naught, and as we divide by c, we get c divided by m. If we divide the whole equation by m, and we have to multiply y naught by omega naught squared on the right hand side in order to get the correct form of that equation. So the standard form of the single degree of freedom oscillator with a harmonic excitation is given here. So you see that you have the acceleration of x, then you have the velocity multiplied by 2d omega naught, which is the damping term, and you have the restoring force of the spring given now by omega naught squared x, and on the right hand side you will find y naught omega naught squared sine omega times t. I would like now to solve that equation in order to compute the displacement x, and then the force, spring force and damping force that acts on the foundation. Well, as you learned in engineering mechanics, when you consider such an equation, a ordinary differential equation, the solution of that ordinary differential equation is given by the general solution of the homogeneous equation, which is obtained by setting the right-hand side to 0, and one particular solution. Regarding the homogeneous solution of the homogeneous equation, what one knows is if there is light damping, and this is the case I would like to consider here, light damping, then the amplitudes of that solution decrease exponentially, and as an exponential decrease is rather fast in time, you have to wait, not very long, then the solution of the homogeneous equation is damped out. So basically what remains is the solution, the particular solution of that ordinary differential equation. So we have to compute one particular solution of that ordinary differential equation, and for that we use a setting analogous to the right-hand side of that equation. So I'm only interested here in the particular solution, as I know that the homogeneous, or that the solution of the homogeneous equation will decrease exponentially, and for that particular solution I look at the right-hand side, and what I find is, well, I use a magnification factor V. I use the same y naught as I find on the right-hand side, because then the factor y naught will cancel, and I use a harmonic function sine omega t, however, minus a phase shift epsilon, because if you use just the sine omega t and you would insert that setting into the left-hand side of that equation, of course, take the derivatives, you would discover that due to the fact that there is some damping, you will get, from taking the derivative of the sine function, a cosine function. And as there is no corresponding cosine term on the right-hand side, you will run into a problem. You would compare the coefficients, but you would not find a non-zero coefficient on the right-hand side. So therefore, you have to introduce a phase shift here for that particular solution. That phase shift is always necessary if there is a first-order derivative here. If the damping would be zero, then taking just sine omega t would be sufficient, because then only harmonic terms, sine harmonic terms, would remain on the left-hand side and also on the right-hand side, and you can do the comparison of these coefficients. So that's the reason that epsilon comes into play here. You know what happens then. You insert that approach into that standard form. So you're setting into that standard form, you take the derivative, first and second order derivative, and you compare the terms in sine omega t and cosine omega t. In order to arrive at formulations in sine omega t and cosine omega t, of course, you have applied the famous addition theorems of trigonometry. The result is then an equation for the magnification factor and an equation for the phase shift. And due to the fact that y naught is part of that approach on the left-hand side, so part of that amplitudes, as I said, as I promised, y naught will cancel and you will not find y naught in that magnification factor. If you would take a v here without having y naught there, then you will see y naught here in the numerator of that magnification factor, of course. This is the standard way to write that equation, and you will find here eta, which is the frequency ratio, the ratio between the excitation frequency and the natural frequency of that vibratory system, of that single degree of freedom oscillator. And also for the phase shift, you will get a classical result, namely that the phase shift is given by the arcus tangent of 2d eta divided by 1 minus eta squared. So these are classical results of basic engineering vibration theory for the single degree of freedom oscillator. But what can we learn from that solution about our system, especially about that connection between the machine and the foundation that we would like to design as good as possible, of course. Yeah? So we will not stop here, but we will use that solution in order to compute the force that with which the system acts on the foundation. That force, the ground force, B refers to the German word Boden, therefore it's FB and not FG here. That ground force is given by the force that is transmitted by the damping element, K, and then the velocity given by the first order derivative of that particular solution here, and finally by the spring force, which is given by C times the particular solution for the displacement. If you insert now the particular solution from the last slide, you will get the following equation. You will get the magnification factor V that has been computed before times y naught, and then you have K capital omega cosine omega t minus epsilon. So this will be the derivative of sine omega t minus epsilon with respect to time. And the capital omega of that inner derivative is located here as an additional factor. And for the stiffness, you will, for the spring element, you will find C times sine capital omega t minus epsilon. This would be the ground force. What we are interested in order to have a comparison with the excitation force is the maximum of that force. So how can we compute the maximum of that force? Of course, we can compute it in the standard way, as it's done in mathematical analysis. So you take the first order derivative, you set it to 0, so you are looking for the maximum of that force, and so on and so on. However, as engineers, we find a better way to treat that problem. What we discover here is something we always discover when we look at a single degree of freedom oscillator with harmonic terms, so that cosine function and that sine function should tell you something. That's something we always do, for example, in electrical engineering. If we have these kind of terms, we represent it in a complex plane. So we represent these elements by a complex pointer. A complex pointer is a vector in the complex plane, and as you can see, that vector has one component, the cosine component, with an amplitude or factor v y naught k capital omega, and a sine component v y naught k omega, v and y naught times c. So the maximum is given by the length of that pointer, which is just the Euclidean norm of that vector, which I would obtain if this is the sine projection and this is the cosine projection of that pointer or of that vector. So the maximum would be the common factor c or y naught v. C is treated as a common factor by dividing k omega by c, and then you take the Euclidean length, so that would be 1 here, and k omega divided by c squared for the cosine component, so for the cosine projection of that length or of that pointer or vector. Yeah. Recall that c times y naught is equal to the amplitude of the force f naught. So we obtain f naught times v, and for k capital omega divided by c, by introducing our standard variables, we obtain it's 2 times the damping, d damping factor, multiplied by the frequency ratio and then squared. The fact that I obtain f naught here is very important, because f naught is the amplitude of that force that acts on my machine, on my rigid block of mass. And it is quite clear that if you increase that amplitude of that force, you increase the force that acts on the foundation. So somehow FB max must depend on F naught. But the question is whether the additional factor that I have here will lead to a magnification of F naught or to a decrease of F naught. So it's not surprising that we get F naught here, but what is of importance is that factor. So in order to get a dimensionless representation, we divide FB max by F naught. So this is done on the next line. So if we divide FB max by F naught, and if we insert for the magnification factor V the classical solution from vibration theory, namely the denominator here, we get the following equation. The numerator comes from that factor here, 1 plus 2d eta squared, and then the square root, that's here. And the denominator comes from the magnification factor. Now the question is, what can we learn from that equation? Especially, what can we learn about how to choose the stiffness of that spring, so how to adapt that spring in order to have a good vibration isolation. So in order to get a small ratio FB max by F naught maximum ground force by the amplitude of that external excitation. So in order to discuss this, I will sketch that solution, and of course there are several figures that I have to sketch for each value of d, so I put them in one figure. I assemble all these figures for varying values of the damping. What you can see is that you get resonance. So it's quite clear that if you manipulate C, you should avoid that frequency ratio eta of 1. So let me repeat that by manipulating C, you change eta because you change the natural frequency of that system that contains the machine as a mass and the foundation and the connection between machine and foundation. So by changing C, you adapt the natural frequency, and by adapting the natural frequency, you change the frequency ratio. So you can see that there are basically two ways to arrive at a small ratio of FB max by F naught. The first one is, and that's a standard answer to the question about vibration isolation. The first answer is make the connection between the machine and the foundation as soft as possible. If you make it as soft as possible, you increase the value of eta, theoretically at least, until infinity, so to very large values of eta. Then you are here and you can see that that ratio theoretically drops down to values that are very small, even close to 0. However, sometimes that's not possible because that connection could, for example, break. There could be some kind of rupture, or there could be some kind of other unwanted effects by making that connection as soft as possible. For example, the static displacements might be too large, it might be unwanted. No? So if you consider a building, for example, you cannot make the foundation as soft as possible. That would simply not work. So then we come to the, I would say, static solution. The static solution can be found on the opposite side. If you make that connection as stiff as possible, so nearly rigid, then eta is close to 0, and then of course you get forces for the ground force, for the maximum ground force, that are very close to F naught. They are a little bit larger, but not much larger than the excitation amplitude. So in this case, it's not possible to reduce the excitation amplitude, but at least the increase is not very large. So either you have a very stiff connection or a very soft connection. There is one interesting point, maybe you have discovered it already in that figure, namely it's that point here. You can see that independent of the damping, all these curves will cross that point here, and that point is very important because that point belongs to the ratio of 1. So it's the point that if you have larger values of eta, so if you are beyond that point, you will have a true reduction of the amplitude of the external force acting on the machine. So you get really a reduction of that force. So the question is where is that point, eta, and why is there just one single point for all these curves? So maybe you guess already where that point is, because it's very close to 1.5, and you know that the square root of 2 is very close to 1.5. So let's see this. How can we compute that point? Well, you can see that that point corresponds to a ratio of 1. A ratio of 1 is obtained from that formula if the numerator and the denominator have the same magnitude. So we equate the square, of course, of the numerator and of the denominator here, and compute that value of eta, which is then denoted by eta naught, the solution of that equation. And as you can see already from equating the numerator and the denominator is that the term containing the damping cancels on each side of that equation. So the solution will be for sure independent of that damping factor. That's shown on the next line. So if we cancel that term, we just get a 1 on the left-hand side, and we get 1 minus eta naught squared on the right-hand side. And if we solve that equation for eta naught squared, we easily arrive at the solution eta naught is equal to square root of 2. So all the curve pass through that point eta naught equal, or eta equal to square root of 2, and corresponding to a ratio of these forces equal to 1. Beyond a frequency ratio of square root of 2, independent of the damping, you will find a reduction of the amplitudes of the forces that act on the machine. If you look at the maximum force that is exerted on the foundation. So that's a very interesting result. However, that result has been obtained for the case that the external force acts directly on our rigid block of mass, which represents the machine. For many machines that are of interest in machine dynamics and also for engineers, we have some kind of rotations and some kind of imbalances. So the question is, what happens if we consider a rigid machine where the excitation is due to an imbalance, so to a rotating element, to a rotating mass force? Will we rediscover this result, or will we get any other result? Let's see. Let me study this example. So let's consider again our rigid machine, so our rigid block of mass, but here the excitation is due to a rotating mass point, so a rotating imbalance. Again, we have studied this example here as a single degree of freedom oscillator in engineering mechanics 4. So the equation of motion should be known to you, and also the solution theory, so how to derive the particular solution, should be known to you. Basically, what you see is the inertia term changes because we do not have to take only the mass m into account, but also the small mass element m naught here, so the imbalance, so the total mass will be m plus m naught times the acceleration of x. Then we have the damping term, we have the stiffness term, and on the right hand side we have the other part of that acceleration, which is just m naught r omega squared sine omega t. Again, dimensionless parameters are introduced, but now of course we have to take into account that additional mass m naught by the in the definition of these dimensionless parameters. You can see that the natural frequency changes a little bit. So it's now c divided by m plus m naught. Also the equation for introducing the damping factor changes a little bit because we divide by m naught. And also the term for y naught is now a little bit different. In the numerator we have m naught times r, and in the denominator we have m plus m naught. This leads me to the standard form, and that standard form is just acceleration times damping term, which is now written in the standard parameters 2d omega naught x dot as before, and omega naught squared times x. So as you can see, in the left hand side is unchanged, it's the same as before, but the right hand side is changed a little bit, namely it's written now as y naught omega naught squared eta squared sine omega t. So if for the particular solution the approach is now x equals v y naught sine omega t minus epsilon, for the magnification factor what we obtain is here v is equal to eta squared 1 minus eta squared squared plus 2d eta squared, and then we take the square root, and eta is again the frequency ratio, so the ratio between excitation frequency, which is the rotation frequency of that mass point, divided by the natural frequency. And for the phase shift, we find that the phase shift is again, so it's unchanged, it depends on the left hand side of that equation, it's the tangent of 2d eta divided by 1 minus eta squared. So the question is, if we study now the force, the ground force as before, and we study the same situation as before. Do we get the same result, or is this the result somehow affected by the different magnification factor? So let's do that. Let's look at the force on the foundation. And of course, the equation for that force is the same as before. So we have the damping term here, and then the stiffness term from the spring stiffness. And again, we find that that equation looks the same as before, and we are interested in the maximum of that ground force. Well, in order to obtain that maximum, we proceed as before. So we have Cy0 V 1 plus 2d omega squared. However, what we have to insert now is here the magnification factor capital V for the excitation by a rotating mass force, so as in the slide before. So we have to take that different magnification factor into account here. You can see the difference is now that tiny eta squared that I wrote here. Now that would be the equation. Now let's study that equation, and you see that the first thing is, well, this is the equation for the maximum ground force. But as we have learned from the example that we studied before, namely the external excitation that acts directly on the mass, we have to consider the dimensionless ground force. And this is a key question here. How do we obtain the dimensionless ground force? And basically, there are two ways to obtain the dimensionless ground force. The first one is, as before, to take C times Y0. C is the spring stiffness, Y0 represents some kind of displacement, so the product represents a force. If we divide Fb max by that force, we obtain, of course, a dimensionless quantity. So this is done here. You can see what you get is something that is different from what you had before, because now the magnification factor is different, so you get that eta squared here in the numerator. The interpretation therefore changes. What you can see is that now the static case, so having a very, you would say, a very rigid connection, so eta equal to 0, leads now to a reduction of that of these amplitudes. However, for the opposite case, so you would say a very soft foundation, so very large values of eta, you will be at the opposite end, and you will see that there, depending on the damping, you could have very large forces, two forces that are close to 1 but always larger than 1. And you see that there is again a point where the solution becomes independent of d, and now this is again the point eta equal to square root of 2, but the value of that ratio changes. You can see this directly if you, in your mind, if you equate the numerator and the denominator, you can see that it's again independent on 2d eta if you equate the two terms. However, there is the additional factor of eta squared here, and for eta equal or eta naught equals square root of 2, this leads to an additional factor of 2 here, so therefore that value changes from 1. However, that interpretation as changing the stiffness is not correct. Look at your ratio. If you change the stiffness here, then what you change is again the denominator of that ratio. So by changing the stiffness, the left-hand side is affected. So basically in that diagram, what you see, you study the effect of changing eta. Changing eta, that effect can be obtained by changing the natural frequency. Basically, as the mass of your machine is usually fixed, that is obtained by changing the stiffness of that connection. However, you change the left-hand side. Or you can change that ratio eta by changing the excitation frequency, which is here the rotational speed of that rotor. And basically that's what is displayed here. So this diagram gives you an answer to that question. If I change the rotational speed of my imbalance, of my rotating imbalance, how would this affect the maximum ground force? So you keep the stiffness of the connection constant, but you modify, if that's possible of course, you modify the rotational speed of your rotor and you get that answer. And that answer is, if you are able to decrease the rotational speed of that imbalance to close to zero, and in general this is not possible because you want to have that these rotations, then you will reduce that ground force. On the opposite end, if you have a high-speed rotor, a high-speed imbalance, then in some cases you are able to at least decrease that ratio again, so compared to resonance, for example, but you are always closer, you are always larger than 1. So what is now the answer if you want to change the stiffness and if you want to study the influence of that stiffness here? Well, the answer is we need a different vector here in the denominator. Think of dividing that equation by eta squared. So you have the product of c, y naught and eta squared. And if you do the computation, so this is the figure for varying capital omega, the rotational speed of that imbalance. So if you want to vary c and you want to study the influence of c, you consider here in the denominator c times y naught times eta squared. And if you do the computations with the standard variables, you will find out that this is equal to m naught times r times omega, capital omega squared. So the ratio that you study is FB max divided by m naught r and omega squared. And now you see that the left-hand side of that figure becomes independent of c. And now if you vary eta, you can obtain the variation of eta by varying the natural frequency, and you can vary the natural frequency by varying the stiffness of the connection C. And, well, no surprise, the answer is the same as for the external force that acts directly on the rigid block of mass, so the figure that we have seen before. And the answer is the same as before. If you want to vary C, make the connection as soft as possible in order to get a reduction of the maximum ground force. And if this is not possible, then take that stiffness or make that stiffness as large as possible, so nearly rigid, in order to allow just a small increase of the ground force with respect to the amplitudes of the excitation, which is given here by that imbalance. Well, this is the end of that first lecture on vibration isolation, namely on active vibration isolation for harmonic excitation. So let me summarize the main results. As you can see, we are studying here a single degree of freedom oscillator under external excitation. For us, as there's always some damping, only the particular solution is of interest. We have seen how to derive that particular solution already in engineering mechanics. However, from that particular solution, we are interested in the computation of the ground forces. We compute the ground force, we take the maximum value of the ground force, and we compare it to the amplitudes of the harmonic excitation of our system. We would like to have a reduction of that ratio, and this is possible by manipulating the stiffness of the connection. If the stiffness is very, very soft, we obtain a reduction of the force amplitudes. However, if this is not possible to have such a soft connection, then a very rigid connection would be the second best, I would say, second best solution here. Thank you very much for your attention. In the next video, I will study passive vibration isolation, and I hope to see you there in my next video. Thank you and see you.